Okay, we'll try that again. My apologies. 4.2 is dealing with Newton's second law, F equals ma. Newton's third law is that we're dealing with in 4.3. Newton's third law says, okay, that for every action, an equal and opposite reaction. That's your simplified way of saying Newton's third law. So you have equal and opposite forces. And we call those equal and opposite forces interaction pairs. Okay? So, you can see this well on a rolly chair. Let's use Matthew, if you don't mind being my example back here. Okay? Go stand up. We'll bring you to the front. There's more room up there. I'll leave your jacket so it's easier for him to see. Okay. We're coming up here. Now this chair is not going to work. It's not very rolly. Let's try this one here. This one is not super rolly either, but we'll try it. Okay. It really works well if we have two rolly chairs, and I was going to use these two, but they're both not rolly. So you got to put your feet, yes, either up or on the rails. And the point is, see, this one rolls very, very, very poorly. When I'm pushing him, if I was in a chair, if I push him this way, are you comfortable I would move backward? Okay? I apologize. We should have gotten better chairs we could do this. So I push him, and there's actually a push back on me. And what we're saying is that those two forces are equal. Thank you, Matthew. I didn't work as well as I wanted. Those two forces are equal. How many of you ever shot a gun before? Okay. I shoot a gun, right? Bullet goes that way. What happens to the gun? It pushes back at you. Okay? There are some quite hilarious YouTube videos out there of people who are shooting these very high-powered guns, and the recoil just like literally knocks them over because it's so much force. For every action, there's an equal and opposite reaction. Does that make sense? And again, we call those interaction pairs. So basically, we can say that the force of A on B is equal to the opposite of the force B on A. Again, because physics, we always have to put little letters next to our F's and V's and all that kind of stuff. Okay? So in other words, the force that A is putting on B is the same that the forces B is putting on A, but it's just in the opposite direction. And that's the key behind all of these problems that we're going to do, to combine this Newton's third law with Newton's second law. And we can actually do some calculating. Are you with me? So let's look at this example problem number 4 that's on page 108. A softball has a mass of 0.18 kilograms. And we want to know what is the gravitational force on Earth due to the ball. So this equals the mass of the ball. And we want to know what is the force of the ball on the Earth. And they tell you that the mass of the Earth is equal to what? No, 9.80 would be the acceleration of gravity. What is the mass of the Earth? Look at the problem, friends. I don't expect you to know this number. What's the mass of the Earth? Ten to the 24 kilograms. Okay, so where in the world did we begin this problem? Again, are you comfortable that if I have this water bottle, which is about the same weight, well, it's a little more actually than a softball. If this water bottle is sitting on the table, well, let's pretend it's actually on the Earth itself, right? Though it is on the Earth, just through the table, through the building. Okay? Pretend this is actually sitting outside on the grass, right? Are you comfortable that the earth is putting a force on this bottle? What do we call that force the earth is putting on this bottle? It's weight. It's gravitational pull, right? The gravitational force. But are you also comfortable the bottle is putting a force on the earth? Right? Newton's third law. Equal and opposite forces, right? So whatever force this bottle is putting on the earth, it has to be the same as the force that the earth is putting on the ball. Does that make sense? So we can calculate that, right? Can we calculate the gravitational force that the earth is putting on this water bottle or on the softball in this problem's case? We can. How would we do that? Say again? Cool. I love that. That'd be awesome. That'd be fantastic. Okay? But let's try this. You know, let's do it. Let's try it. So, can I solve for the weight of this softball? I hope I can. Yeah? Okay. So how would I do that? Weight is just equal to force, right? Weight is just another word for force, right, guys? F equals ma. Okay, so the mass of the ball is 0.18. And what is the acceleration of the ball? We're talking about, right? We're talking about gravitational acceleration, so this would be 9.80. So the force of the earth on the ball is equal to, what's this number? $1.9. This is what your textbook says. 1.8, excuse me. Because I've only got 0.18 as my number. So that's in newtons. Are we cool? Absolutely. Want to make sure you heard that. If the force of the earth on the ball is 1.8 newtons, what is the force of the ball on the earth? Equal and opposite, right? So it would be negative 1.8. Does that make sense? Again, force of the earth on ball is equal to the force of the ball on the earth. Right? So if this, the weight, was 1.8 newtons, this has to be negative 1.8 newtons.
Since like gravity is going to be used as a minus, shouldn't this be minus 1.8?
You could use either way. It doesn't matter. We chose to use gravity as being positive. So yeah, I agree with you completely though. Are you with me, my friends? So we've calculated now, this is the force, negative 1.8 newtons. So does the earth actually accelerate because of that water bottle? Well, there has to be some, right? But a teeny little bit. Let's figure it out. So if 1.8, if F equals ma, right? And I want to find A, how would I switch this around? Cool. A equals F divided by m. So, let's try it. Acceleration of the earth is going to be equal to, what is the force? Sure, we'll use our negative 1.8 newtons. And what is the mass of the earth? A whole big, huge number, right? 6.0 times 10 to the 24. All right. So, do your math. Well, no, actually do the division. And I get 2.9. I get 2.9 times 10 to the negative 25 meters per second squared. Yeah, let's put a number on that. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 29 meters per second squared. That was 24 zeros. Sure, but I had to move it one place to get it beyond there. So, yep. So I took the force and I divided it by the mass. In this case, it's the mass of the planet, correct? Because we're talking about how much will the Earth move because of the weight of the ball being on it. Is it moving a lot? Not really at all. Because again, the Earth is slightly larger than a softball. Slightly. Yeah, just a tiny bit more. Right? Just a little tiny bit, like 0.18 grams versus 6.0 times 10 to the 24 kilograms. I mean, it's a little difference. Why is it accelerating? Because there's a force being put on it. No, because again, all the cumulative amount of these forces is just still so very tiny. I suppose technically, sure. But there's other forces happening other than the other side of the Earth that would be pushing opposite of that. I don't think so. It's all a wash. Sure, right. Sure, we do have a negative here, so we could put the negative. I appreciate that. We should have put negative, since we had negative 1.8. Your textbook for this example, they made the gravitational acceleration be negative, so their answer was coming out positive. Either way. Either way. They made, when they calculated the mass of the ball, they made this force to be negative. Right? But I was trying to keep it with this, so it would be negative, our new force. But I just didn't write it down there. Thank you for pointing that out. Are you with me, my friends? And this all goes back to this, right? It all goes back to Newton's third law. If I'm saying that the Earth is putting a force on the ball must be putting the same force on the Earth. But because there's such a difference in mass, they don't nearly move as much. Are we cool? Two more pieces to talk about very, very, very quickly here with you. Over on page 109, we're talking about tension. All right? Tension is just a specific name for a force that a string or a rope exerts. Okay? So this is a terrible drawing of a bucket, right? The force of tension is pulling up. The force of gravity is pulling down, right? So just like our bag of groceries yesterday, right? If my rope can only withstand, let's say, 50 newtons before it breaks, I have to take into account the force of gravity plus the force of tension. Does that make sense? Because gravity is pulling down on the rope. If you accelerate the rope upward, you're putting tension on the rope, pulling it upward. So both of those forces are affecting the rope. Does that make sense? Should we do a quick problem with this so you can see that? So let's say that you've got 4 kilograms of mass in your bucket, right? And you want to accelerate that bucket upward at 0.5 meters per second squared. Right? And the rope only holds 50 newtons. Will the rope break? This is a classic problem. You have one just like this that you do in your homework. Okay? So what pieces do I need to find out? What can I calculate here? Because what forces are acting on this bucket, on this rope? Force of gravity and just the tension, right? The force pulling up on the rope. So let's calculate both of those two forces, right? So what's the force of gravity? That's acceleration. Force of gravity is what? for the mass times the acceleration, 9.8. Right? So the force of gravity, can someone do the math for me? This is not in your textbook, so we have to do some numbers. What's 4 times 9.8? Should be just less than 4. B. No, we do. Yeah, gravity's pointing down. In other words, we're finding force. This is acceleration, and we're using 9.8 for. It's what, Eric? 39.2. Well, let's make this 50.0 so we can use that. Okay? So therefore, this is telling me if you've got 4 kilograms in that bucket hanging on that rope, the rope's not going to break just by holding it. Does that make sense? The rope is stronger than the gravitational force pulling it down. We cool? All right, but then Ben comes and he wants to slowly, because 0.5 meters per second squared is fairly slow acceleration. He wants to lift this up 0.5 meter every second. Fairly slow. Okay? So, how would I translate this now? How would I find out the force that that acceleration provides? If you must. Come on, guys. I apologize. One equation, right? If I want to find force, what equation do I use? F equals ma. All right? So if I want to find force, what's my mass that we're accelerating? 4.0 kilograms. What's my acceleration that this tension is giving now? 0.5. Okay? So someone do that math for me. 4 times 0.5. 2. Good. So the F of t is 2.0. So if I add, because of course the total force is these things together, right? The force net is the force of gravity. No, ignore this. Ignore that. The force of tension. And I put a negative there because they're opposites, right? Does that make sense? So therefore, this must be a negative 39 because it's pulling down, right? It is. We'll talk about that in a second. Yep, we'll talk about it in a second. So therefore, force net is equal to negative 39.2 plus 2.0. Gracious. Plus 2.0. So what's my final number? My force net is equal to? Well, remember I got negative and negative, so they cancel. So I get 41.2 newtons. Does my rope break? No, thankfully. It does not. Okay? You could accelerate that rope, well, almost 20 meters per second squared. And it's still not break. Right. Well, no, not 20. Sorry, 5. Are you with me, my friends? Okay? Tension is just simply a force being pulled by a rope. Nothing special. We just give it a special name because it's using the rope. Okay? The last piece is the normal force. And we have talked about this guy before. The normal force. That's just a force that is perpendicular to a surface. So the normal force is the force that is holding your textbook on your desk right now. That's holding your computer on your desk right now. Because gravity is pulling it down, right? It's trying to make it go into the floor. But what's pushing back against gravity? This normal force. Does that make sense? So I could calculate normal force simply by calculating the gravitational force. And the normal force is just the opposite of that. Does that make sense? It's just simply the force that's opposing, because this is on a surface, right? Because this is sitting here on this desk, gravity is pushing down, the table's pushing up. So therefore the book's not moving. The normal force is the force perpendicular to the surface, right? The surface is horizontal. The normal force is acting vertically. Sure. The normal force of gravity is trying to pull that tower down, right? And the foundation of most buildings are strong enough to oppose that for a period of time. This one is set on the type of soil that's allowing it to sink on one side more than another. So you get this leaning piece. They've actually done some work to shore it up so it won't fall over. But it may eventually.
So, like, with the reinforcement, you said that this was vertical and this is horizontal?
Right. Your surface is horizontal. Your normal force goes perpendicular, so which would be vertical. Oh, sure. If I tip this table the other direction, sure, the normal force would be pushing it that way. But it wouldn't be opposing gravity if you tipped it fully upright, because gravity is going just strictly up and down.
Oh, the surface itself?
The surface itself is giving the force. Because what we'll actually do is we'll put things on ramps, and then we have to break up the forces into its pieces. Part going horizontal, part going vertical.
So the Earth, would that be like normal force or no, because it's round?
Well, it's round in a large enough ball that basically it's flat where we are. Does that make sense? There's a little bit of roundness to it, depending on how far distant you're talking about. You go outside, you don't look and see the Earth and look around. It looks flat, right?
Well,
Yeah.
it's not flat.
No. And if you were doing calculations over a long distance, you'd have to take that curve into account. But for
Where do you draw the line of where you put the
it all depends on the precision that you're trying to measure. Yeah. The experiment that they did that found that there actually are gravity waves. I don't know if you heard about this. They won the Nobel Prize a couple years ago for the fact that they found these waves of gravity, right? For them, they used these lasers that were over kilometers, that they were measuring this distance, right? And you were talking about changes in nanometers over that distance. There they had to take into account the curve of the Earth. Because they were measuring it so precisely that that little bit of curve actually made a difference. But for you and I, nah, we don't. We don't do anything that precise. Does that make sense?
Yeah.
But maybe someday. Maybe someday. Whew. Are you with me, my friends? The key point for this chapter, section 4.3, the key point is that F of one force is equal to the opposite force in the other direction. Interaction pairs. If I'm pushing on this table, the table is pushing back at me. If I'm standing on the earth, putting a force down onto it, the earth is pushing back up against me. If I push Kirsten, Kirsten pushes me. Like the opposite of the Bible verse I just read. Isn't that interesting? Yes, ma'am. Please. Here is your assignment. 4.3, numbers 28 to 33. I would love for you to finish that one for the moon day. And you have opportunity to work at this moment. About almost 10 minutes.